Okay, thanks so much for having me. I'm excited to share some of my PhD research with you all, and happy to be joining from 9 a.m. in Anchorage, Alaska. I'm going to talk today about automated avalanche terrain mapping. This is a big part of my PhD research that I've been working on at Simon Fraser University with my supervisors, Pascal Hageli and Yves Buehler from the SLF in Davos. Before, let's see if I can go to the next slide. Before I get started, I just want to acknowledge that the SFU campus, as well as the study area for this research, is located on the unceded territories of the Canadian First Nations people. And if you want to learn more about it, you can go to native-land.ca to look at some of these maps of the traditional lands of Canadian First Nations. So, overview of my presentation, I'm going to start off by giving a little bit of background information about avalanche hazard mapping and the attempts to automate avalanche hazard mapping over time, and some of the kind of fundamental knowledge that's really required to understand the concepts I'll be introducing in the research presentation. And then I'm going to talk about a project that we've been working on just south of Revelstoke in the Columbia Mountains in British Columbia to apply what's called the potential release area model to more forested mountain region. And then I'll wrap it up just by giving some broad picture conclusions and talking a little bit about directions for future research based on the results that I've presented. Okay, so I think probably you're all familiar with the traditional practices of avalanche hazard mapping. These are commonly used for zoning residential buildings or infrastructure or commercial buildings. And typically, this process involves several local experts who are going to evaluate an avalanche path or several avalanche paths using a variety of different methods, including tree ring evaluation, like you can see in the picture on the top right, avalanche simulations like the RAMS model that you can see in the bottom of those images, and the output is generally these different color zones depending on avalanche return frequency and the amount of force that an avalanche is expected to have. And those are super useful for understanding avalanche hazards for infrastructure. But because they're so redundant and so thorough, those practices are really not feasible to do on a large scale across a mountain range scale or even an entire country. So all the way back since the mid-90s, there's been an effort to take some elements of the hazard mapping procedure and automate them so that we can scale them up and use the data over a much broader region. The first paper that I found for this was published in 1995, so it's certainly not a new idea, but the quality of the data available to generate the automated maps was really low back in the 90s. And so in the last decade or so, the quality of the input data has really improved. So potential for applying these techniques in a lot of different areas in the world is kind of exploding right now as new data becomes available. And the foundational data set that's really required for any of these automated avalanche mapping methods is the digital elevation model, or DEM. And this is just simply a digital representation of the Earth's surface. So it's like a digital topo map where the entire area, so this example that I'm showing is just a square area of mountainous terrain. And the entire area is broken up into individual pixels. So every cell has a different value for the elevation in that location. And you can end up representing it like this, where we're seeing different heights of the different cells. The resolution can range anywhere from 1 meter on the highest resolution end, all the way down to 30 meters for low resolution data. But the advantage there is that 30-meter data tends to be available for free worldwide. So there's trade-offs as far as cost and availability with the different resolutions. And there's several different methods for creating these. I'm not going to go into in too much detail, but a lot of different countries will have different quality products available. So in Canada, for example, the best quality DEM for the entire country is only 20-meter resolution. So it's really doesn't meet the criteria that we need for doing automated avalanche terrain modeling. So I'll get into a lot more in the research presentation. The other really fundamental data set that's required for automated terrain mapping is a land cover classification. And this is a remote sensing method that uses some kind of a sensor. The example that I have here is a satellite spot 6 sensor. So it takes pictures in the visible and infrared wavelengths. And we can essentially use the reflectance properties of the ground surface to categorize the land cover into different classes. So some examples would be forest, water, ice, rock, or agriculture. Each one of those is going to have a unique spectral signature that allows you to classify it just based on how it's reflecting back the sunlight. And these kind of calculations can be done using sensors from satellites or airplanes or even drones or UAVs. So those are kind of the two fundamental data sets that you need to understand to kind of go further down this road of automated avalanche terrain mapping. And the foundation for all this automated terrain mapping is called a potential release area model. And essentially what we're trying to do here is identify where avalanche start zones are. So typically, this is the first step in kind of a chain of different models where we're going to identify start zones and then maybe simulate runouts from those start zones. But any errors that happen in this potential release area or PRA modeling part are going to trickle down into all the other parts. So it's really worth focusing time and energy on honing in this potential release area model before moving on to the later steps. And how these work is they use terrain characteristics like slope angle, curvature, roughness, or wind shelter, and you can see some of those in that image, to classify where avalanches are possible. And slope angle is by far the most dominant input parameter here, and the others are just kind of trying to fine tune where the start zones are. The last thing comes in, you could set up your potential release area model to not look for start zones that are in forested terrain if you think the forest is too dense to produce avalanches. And that's the method that's been used traditionally. My research really focused on bringing a little bit more nuance into the forest cover modeling part of this. And yeah, I'll discuss it in depth in just a moment. A couple different examples of potential release area models. The one that I'll focus on is this from Yves Buehler, which was originally developed in 2013 and then updated in 2018. And it used slope, curvature, and roughness to calculate potential release areas. And the real advantage of this model is that it was validated in the Davos region in Switzerland using a data set of over 2,000 avalanche observations. So the ability to fine-tune the input parameters to match the observed conditions is much greater here than in any other areas that I'm aware of. And there are, just so you're aware, there's a whole bunch of these. There's probably a dozen different types of potential release area models, but the two that I've used mostly and that are most kind of up to date are the Yves Buehler's one from 2018 and this one from Weitinger in 2016, which is very similar, except that instead of just having a binary, either it's a start zone or not a start zone, the Weitinger model gives you an output from 0 to 1, the probability that it is a start zone. So it's a little more nuanced, but we'll be focusing on the Buehler PRA model for the rest of the talk. So one application that this can be used for, this is just a screenshot of a figure from Davos where you have on the far left the actual hazard map for the region. And then the middle panel and the right panel are the output of what they call hazard indication maps. So this is a combination of the potential release area model and then using the output of the release area model to then do RAM simulations or runout simulations and figure out the extent and force that could be produced by avalanches. And the difference between those two panels, the one in the middle uses that forest cover mask that I've been talking about to eliminate avalanche release in forested terrain. And the one on the right doesn't do that. It allows release areas to occur anywhere, regardless of forest cover. And you can see how dramatic the difference is there. So really where my research fits in is trying to find a middle ground between totally eliminating all forested terrain and allowing release areas to be calculated just as they would be for alpine terrain in the forest, because it's really overestimated in the right image and underestimated in the left image. So we kind of want to find that middle ground. So I'll jump into the research now. The kind of main themes I'm going to talk about were developing the input data sets required for this type of potential release area modeling in our study area. Like I said, the freely available data in Canada is very low resolution, so we had to do a lot of work to develop these data sets. And then I'll discuss the updates that we made to the PRA model to better capture forest density, and a local validation that we had to undertake because we didn't have this large data set of observed avalanches. So we had to use the local knowledge of some guides that we've collaborated with to create a validation data set. And then finally, I'll just show the final output in the runout simulations that we calculated. So this is our study area. It's the guiding tenure of CMH Galena, which is a mechanized guiding operation. It's about an hour south of Revelstoke in British Columbia, located in the Selkirk Mountains. The snow climate there is kind of an intermountain transitional snow climate, and surface hoar weak layers are a very common issue here. And that was kind of one of the defining characteristics of why we needed to adapt the PRA model to better fit both the terrain and the snow climate in our study area. You can see the purple polygons in this map are all the different ski runs that are guided on in this operation. And the yellow highlighted runs are the 5 that we use to validate the model. So that's where most of the data that I'm going to present comes from. And then we applied, once we validated it in those 5 runs, we applied it across the whole tenure. So to develop the input data sets, we looked at a lot of different options, and we decided to create our own DEM using satellite stereo imagery. And this is a fairly technical process that essentially just looks at the same image from 3 slightly different perspectives and is able to create a digital elevation model based on the difference in the geometry between the different images. So we created a 5-meter DEM using an open source tool called the AIM Stereo Pipeline. And this was the cheapest alternative that we could find to create the necessary DEM resolution, but it was still pretty expensive. And then we used a satellite called Rapid Eye, which is again a 5-meter resolution to develop our forest cover classification. And I'll show you what those look like. So this is our DEM. The upper right is what the DEM looked like, the lower resolution version, where the free Canadian version. You can see how smoothed out it is. You can't really determine gully features or smaller scale slope features, especially compared to the bottom left. So this is one little section of our spot 6 DEM. And you can just visually see how much more accurately it's able to capture terrain features that are relevant for avalanche release. So really the foundation of doing this automated terrain modeling is developing these high quality input data, or if you have them available, then a lot of the hurdle of applying them is taken away for you. This is what the satellite image looked like that we did the classification based on. It's the false color image. So the dark reds are forest. The really bright reds are faster growing vegetation like grasses or shrubs. And then the grays and whites are rock and ice. You can see this is our classification. So all the green pixels are areas that we've designated as forested regions. And those are our 2 kind of foundational input data sets. Now I'm going to talk a little bit about how we changed the way the PRA model worked to account for forest density a little bit more. So this is kind of just a basic workflow. I just explained step 1, we did this classification. The forest mask is what we just saw. So each pixel is determined to either be forested or not forested. And then steps 3 and 4 were what we added to the PRA model. So what we're doing is we're looking within a 5-cell neighborhood, which would be 25 meter by 25 meter neighborhood. We're looking at how many pixels within that neighborhood are forested, and then we're reclassifying the data to kind of generalize it a little bit more. So it's not quite as sharp of a boundary between forest and not forest, it's more of a transition from dense forest to less dense to more open terrain. And we feel like that more realistically captures the way the snowpack is influenced by changes in solar radiation or changes in winds that can happen at the boundaries of forested terrain. So this forest density layer, again, this is just our raw forest classification. And then when it goes through that neighborhood function, it looks more like this. So the lighter yellow colors are lower density forests, and the dark green are higher density forests. So this gives us a little bit more of a nuanced perspective on how dense is the forest cover. Again, we're just using satellite remote sensing, so we don't actually have any information on the forest density from the ground because the scale of the study area was too large to do that. So this is the best we could come up with for kind of a remote sensing hands-off approach that could be applied on large scales. And then essentially what we're going to do in the next step is we're going to change, as I said earlier, the slope angle really is the most important factor for determining how the potential release area model works. So what we decided to do is change the minimum slope angle threshold to be a start zone depending on the forest density. So this is an example of what that looks like. We call this the slope scalar function, or the forest slope scalar function. And these are different input parameters that you could designate for the PRA model depending on your region. But essentially, you can see along the bottom axis, we have the different forest densities: open, sparse, moderate, dense, and very dense. And then by increasing the scalar function, you can increase the slope angle minimum for the more dense forests. So for example, if we have a slope scalar of 1, which is kind of a light teal color right in the middle, for open terrain, the minimum slope angle threshold would be 30 degrees. For sparse, it would be 31, moderate 32, dense 33, and very dense would be 36, or somewhere roughly around that. Or sorry, 33 and 34. I started looking at the wrong line. But you get the idea. You can kind of control how the PRA model interprets the minimum slope angle in forested terrain using this pretty simple function. So these, just to clarify, we just added these to the existing PRA model that was created by my supervisor, Eve Bueller. So it's an optional function that can be included if you feel like it's appropriate for your terrain. If you have mostly non-forested terrain, then you don't have to include these inputs. But if you have densely forested terrain in part of your study area, then you can play around with these different parameters to change how the model interprets the forest. The next kind of big component of our research was coming up with some kind of a validation data set. And as I said earlier, we didn't have a large data set of observed avalanches like they did in the Davos research. So we worked with 2 longtime guides for this tenure to develop a little bit more of a nuanced validation data set. What we discovered is that asking somebody who's worked in an area for multiple decades to map all the start zones is quite challenging. The changes in start zone extent depending on conditions and the snowpack year, all those variables makes that quite difficult. So we developed a little bit more of a fuzzy method where they can draw a polygon and then assign within that polygon what percentage of the area is a potential release area. So if you look on the map on the right, the dark reds, that's where the guides were very confident. They said, okay, these are 100% start zones. We know these release often and we see them often. And then as you move more into the yellow and white colors, the percentage of release areas within the polygons is lower. And it gives the guides flexibility to not have to identify specific slopes, but they can identify more general regions, and then we can compare that output to how the potential release area model sees those same polygons. So this is really the foundation for how we optimize the PRA model for our tenure or for our study area. And it changed the validation calculations quite a bit from the original research in Davos. So using those polygons, we did a grid search method, which essentially is a fancy way of just saying we tested a whole bunch of different input parameters. You can see them in these plots on the right. So everything along the bottom axis are the different input parameters we tested. And then the black vertical bars show the final parameter that we landed on. And there was no combination of parameters that perfectly captured all the polygons. So we decided to intentionally bias the model towards over predicting so that we were more likely to capture an area that might not be a start zone versus missing an area that is a start zone. We felt like that was a more kind of conservative approach to take for this type of modeling. And in the end, the only input parameter that we changed from the Davos defaults was the slope angle minimum. So the other ones, the slope angle maximum, curvature, the ruggedness, we all kept the same as what they had in Davos because our data set didn't show any significant improvements either way by tweaking the parameter. So we kept those the same, and we only changed the slope angle minimum, and then of course the parameters that we added, forest density and forest slope scalar. This is what all the 5 different validation runs that we use look like. And they're all kind of facing downhill. So downslope direction is towards the bottom of the map. And they're color coded based on how accurate the PRA model captured compared to the guide's evaluation. So the kind of beige color means that it was accurate. The area of potential release area matched what the guide saw. And then the blue colors are overestimated and the red colors are underestimated. So you can see this changes quite a bit depending on the run. And a lot of that comes down to the forest characteristics on these different runs. So for example, the upper left panel, panel A, has a lot of severely overestimated area because the forests in these areas were very tightly packed, smaller trees, which had a lot more anchoring effect than some of the forested terrain in other regions. So there's definitely some room for improvement in our methods, but overall, we were pretty happy with the improvement that we saw versus the previous methods. So speaking of the improvements we saw overall, compared to the Buehler PRA model defaults from Davos, we saw a decrease in absolute error by 3.2. We improved the percentage of the polygons that were actually accurately captured by almost 12%, percentage points, excuse me. And then we had a lower percent of underestimated polygons by almost 15% percentage points. So these were significant improvements. In general, PRA modeling is kind of a field of very marginal gains, but we felt like the ability to improve by these margins just by adding some simple forest functions was really made a substantial contribution to the model chain. And you can see what the different model outputs look like. So this map in blue shows what the extent of the potential release areas would be using the defaults from Davos. And then the pink color shows by altering the slope angle minimum down to 28 degrees from 30, we expand the potential release area into different terrain, which is a pretty substantial increase. And then we further expand. The purple color shows forested areas that have been determined to be potential release areas, none of which would have been captured by the Buehler model using that forest mass technique. So just in terms for this portion of our study area, there's a significant difference in the extent of potential release areas by including forested terrain. The next step before you can do the runout simulations is to convert the raster output of the PRA model, so that kind of gridded type of data, into polygons. And Yves Buehler developed this method using object-based image analysis to convert the raster PRA output to polygons automatically. And in our study area, we ended up with almost 210,000 potential release areas. And we used a release depth of 50 centimeters across all those study areas to estimate runout. Here's the output from the RAMS modeling that Yves did for us. On the left, we have runout debris height. In the middle is the pressure. And on the right is the max velocity. And these are combined from many small avalanche paths into a kind of a mosaic of all the different runout models for these two runs we're looking at, but we have this for the entire tenure. So here's just an image of what the final data set looks like. So each one of these little purple puzzle pieces is an individual release area identified by the model. And then now underneath that, you can see the runout zones calculated through the RAM simulations. So this is kind of our final product. And in our case, the goal is to produce these to analyze a data set of GPS tracks to start understanding decision-making in avalanche terrain, but could also be applied in different contexts like we discussed earlier. Okay, so moving on. So in summary, the key components for doing any kind of automated avalanche terrain mapping, the first one is high resolution DEM data. And that it's really hard to get around that one. High resolution forest cover data is necessary if you want to kind of do what we did and take a more nuanced approach to how forested terrain impacts the avalanche release. And then the third one is some kind of a validation data set. Some of the key challenges are the data cost of acquiring high resolution DEM is really high if they're not available. And the high quality validation data is not really widely available. Also, the computer processing for large scale PRA modeling can be pretty intense, especially for the RAM simulations. Unfortunately, I was supposed to go to SLF for 3 months in the summer of 2020 to do this research myself, but as we all know, COVID kind of put a stop to that. 2020 was a weird year, so Eve ended up doing this research for us. So I wasn't as hands-on with the RAMS modeling as I would have hoped to be. Just to highlight kind of our approach for this local validation, we developed a custom online mapping tool that you can see there in the bottom right, where the guides could go in and look at a variety of different base layers. So here they're looking at satellite imagery. We also provided them with slope angle layers or just topo map kind of layers with contour lines, as you can see there. And that's kind of the basic data sets that they had to run through the terrain, draw the polygons, and then fill out kind of a pop-up form with the percentage of the area that's avalanches and a few other fields to give us more information. So that's kind of the nature of how we collected the data set. It took us quite a bit of back and forth with the guides to develop this method. But in the end, I think we both felt pretty happy that we could accommodate some of the restrictions of relying on essentially their recollection of the terrain and their experience in the terrain to create this data set, but also still captured in a meaningful way statistically where we could validate the model. So I think this could easily be applied in other contexts. So it doesn't necessarily have to be guides, could be local avalanche forecasters or ski patrollers that are familiar with the terrain. And, we have a wealth of experience and expertise out there in our mountain community. So being able to harness that to improve the accuracy of these automated models is a really powerful tool. And finally, some applications. So the SLF has developed some tools. I believe it's called the White Risk Trip Planning Project. And you can use, the foundation of it is these potential release area and runout models. And then they use quite a few other data sets like potential for remote triggering and fall, like hazards of falling in the terrain, to provide a trip planning resource that you can use to identify kind of crux points along your route, or plan where you might want to camp, or plan routes through the mountains using more nuanced information than just a slope angle map like we have traditionally used. I talked about this previously, but these methods can also be used to create at least a first draft of a hazard map or a hazard indication map, which could be useful for future development or in more remote areas that don't have existing avalanche hazard mapping available. And then finally, the application that we're going to pursue is to use these models to understand decision-making in avalanche terrain based on GPS tracking. So you can see in that image on the right, the combination of the release areas, the run out, the forested terrain, and the GPS tracks are the black lines. So those all hopefully will come together to provide us some information on what drives professional guides to make decisions in different conditions. Just a little preview into what that might look like. So we have my supervisors collected over 10,000 GPS tracks over the past 5 seasons from this operation, CMH Galena. And we did all this work to develop the PRA and runout simulations as a means to provide more nuanced information about terrain characteristics that could influence those GPS tracks. So these images on the right are just kind of samples from our data exploration. So we've selected 4 kind of distinct routes within this one run. And then the plots on the bottom just show how the terrain characteristics vary depending on those different runs. And yeah, I'm not going to get too much into it because it's still a lot of exploratory research and gets pretty muddy pretty quickly, but I'd be happy to answer any questions people have on it. Some of the other things that we're going to look at in combination with this are things like weather, avalanche conditions, and the guiding operations, and how those all kind of play together to affect the decision-making and terrain management of professional guides. So with that, I just want to say thanks to the supporters of the SFU Avalanche Research Program and our GPS study, and I'd be happy to take any questions that anyone has.